right. So first of all, before we get into section 6.2, is there any questions about the 6.1 homework? I know it's semi-complicated. There's kind of a lot of stuff going on within the homework assignment. Are there any questions about this homework assignment? Is there anyone you guys had trouble with? Anybody? What do you think? It's not, this section especially, it's not extremely hard. It's just very tedious, right? There's a lot of very small steps. A lot of really small things you have to do. You have to make sure you do them correct or else the whole thing's going to be wrong. So it's like, like I mentioned, it's like cooking a big dinner. Not any one thing is particularly difficult. It's just a lot of steps you have to do in the right order in order to do it correctly.
So on that one, where it says sample up there at the top, you do 1 plus 1 divided by 2. Is that how you get the mean?
Yes, for each one.
For each
1 plus 1 divided by 2. So the mean for that will be 1. Here it will be 1 plus 2 divided by 2. So it will be 1.5. So let's just go ahead and look at this one. Because the section 6.2 is really pretty short. As far as in material to cover, the ideas in 6.2 are pretty dense, kind of like this section.
Yeah, but then if you put one answer in there all wrong, and it doesn't tell you
Right,
wrong.
right, and that's the hard part. Yeah, it doesn't say your probability for 3.5 is incorrect, right? It just says that something's wrong. Okay, so consider the population described by the probability distribution. So this is the distribution to start with, all right? And then we're pulling samples of 2, right? We're observing the random variable twice. So what are all the different outcomes? So it says the random variable is observed twice with independent observations. There's that word independent again. Even though I didn't test you over independence, we sure see it a lot. All right, we've seen it a lot from this point forward. So that's why I spent time covering it in that section. Remember, independence means the outcome of the first experiment has nothing to do with the outcome of the second experiment. That is not mutually exclusive. Mutually exclusive means the outcome of the first experiment and the outcome of the second experiment have absolutely nothing in common, which is not the case here. Because we see plenty of times where we could have 1, 1, we could have 2, 2, we could have 3, 3, and we could have 4, 4. All right, so all those show that it is not mutually exclusive. All right, so what I want to do here is, let's go ahead and determine, I'm going to write out my samples, and then I'm going to write out my X bar for each sample, all right? Because in the section 6.2, that's what we're going to have to do a lot of, okay? So there's what? 4, 8, 12, 16 of them. So there's 1, 1, 1, 2, 1, 3, 1, 4. Then we have 2, 1, 2, 2, 2, 3, 2, 4. Then we have 3, 1, 3, 2, 3, 3, 3, 4. I'm starting to run a little bit out of room here. Let me kind of put these together a little bit more. 1, 1, 1, 2, 1, 3, 1, 4, 2, 1, 2, 2, 2, 3, 2, 4, 3, 1, 3, 2, 3, 3, 3, 4, 4, 1, 4, 2, 4, 3, and 4, 4. All right, so this is my observations, right? That's my sample right here. So these are all the different possible outcomes. Then let's go ahead and find our X bar for each outcome. Find the average of each one. So here, like you said, Crystal, you add 1 and 1 and divide by 2. We're just going to sum these two values and divide by 2. Right? I kind of want to, well, I'll try and keep them as straight as possible. So 1, 1, the average is 1. 1, 2, 1 plus 2 is 3 divided by 2 is 1.5. What's the mean for 1 and 3? 2, right? 4 divided by 2, which is 2. 4 plus 1 is 5 divided by 2 is 2.5. 2 plus 1 is 3 divided by 2 is 1.5. 4 divided by 2 is 2. 5 divided by 2 is 2.5. 6 divided by 2 is 3. 4 divided by 2 is 2. And so on. So here we go. Keep going. 5 divided by 2 is 2.5. 6 divided by 2 is 3. 3 plus 4 is 7 divided by 2 is 3.5. 2.5. 4 and 2 is 6 divided by 2 is 3. 7 divided by 2 is 3.5. And then 8 divided by 2 is 4. All right. And then notice here's the probability of each experiment, because our numbers 1 through 4 do not have equal probabilities, right? If each of those were 0.25, then each of these probabilities in this table would all be the same, right? They'd all be 0.125 or 0.13 with rounding. But 3 is the thing that shows up the most. So any of these pairs that include a 3 are going to have higher probabilities than the other ones, right? Because 3 shows up 0.4 of the time, right? So then we need to go in and we can write out our... So the probabilities are listed right there, right? So let's look for the x bar of 1. And notice all these top ones, they move up. They go 1, 1.52, 2.53, 3.54. So this very first one has to be 1. All right? Now what's the probability of achieving an average of 1.5 with my sample? So that's going to be the probability of this point plus the probability of this point. Right? Do we see that? So it's going to be the probability of this sample point, because that's our mean is 1.5. So what's the probability of 1, 2? 0.06, right? And what's the probability of 2, 1? 0.06.
So 0.12.
0.12 would be the probability of getting a mean of 1.5. Right, good job. So this is 0.12. These ones I don't really even need to do any math, right? This one I know is going to be 2.5, and this one I know is going to be 3. So let's find the probability of our sample mean being 2. The probability of our sample mean being 2. So how many are there? There's 1, 2, 3. Right? So we need to count this one, and then this one. So we need to add those 3 probabilities together, whatever they are. So 1, 3, the probability is 0.08. 2, 2, the probability is 0.09. So 0.08 and 0.09 is 0.17. And then here for 3, 1, the probability is 0.08. So we're adding 0.08 plus 0.08 plus 0.09. All right? So 0.16 plus 0.09 is 0.25, right? Now the nice thing about this distribution is I really only have to find the probability for one of these, because I can find the last one by adding them all together and subtracting from 1. Right? Because all these probabilities added together need to equal 1. Is that correct? You guys follow that? Right? And I'm going to go ahead and just do 4, because I see 4 only shows up 1 time. So it'll be easy to calculate the probability of getting a sample mean of 4. What is it? Down here at the end. 0.01. So the probability of my experiment of observing 2 independent trials of the mean of my 2 points being 4 is 0.01. Basically, I have a 99% chance of that not happening. And then now I can add together, rather than add together the probabilities that are equal to 3.5, which I could do, I can add them all together and subtract from 1. So a couple different ways to do it. All right. But notice 3.5 only shows up twice. Right, you see any other sample means that are equal to 3.5? It's just 3, 4, and 4, 3, right? So what is, so the probability of getting a 3, 4 is 0.04. The probability of getting 4, 3 is 0.04. So I add those two together and get 0.08. Now what I want to do is let's add all those probabilities together and make sure they equal 1. Right? They have to sum to 1. So try that. And you can do it in your head if you want, or in your calculator. So 0.04 plus 0.12 plus 0.25 plus 0.28 plus 0.22 plus 0.08 plus 0.01. Enter. And you should get exactly 1. So this one didn't give you the X bars like we looked at in our book for that craps experiment. So really what I could do is write this and then go ahead and write out the whole chart and put P of X. What did I do with that marker? I could have went ahead and put probability of X bar and then just listed those probabilities that were there. It made it a little bit easier to add them together. But you didn't really have to. Okay? So there's that. Let's check and make sure I got it right. Okay, good job. There's the first step. Now it says construct a probability histogram for the distribution of X bar. Now, which one of these means has the highest probability? 2.5. So I would definitely expect the bar in the center to be the tallest. Everybody see that? There needs to be 7 bars as well, right? Because there's 7 different values. 1, 2, 3, 4, 5, 6, 7. So this one's not going to work, and this one's not going to work because they only have 4 classes, right? We need 7 classes. But if we go in here and look at this one, there's 1, 2, 3, 4, 5, 6, 7. Is the probability of the outcome that's to the left of 2.5, is it slightly higher than the probability of the outcome to the right of 2.5? It is, right? Because this one's 0.25 and this one's 0.22. So I would expect the bar that's associated with 2 to be a little bit taller, which is exactly what's going on right here. Everybody see that? And then notice for 4, our probability is very, very small, right? It's 0.01. So that's our answer for this one. Down, check answer. All right. Bless you. What is the probability that X bar is 2 or larger? How would I answer that question?
Add 0.25, 0.28, 0.22, 08, and 01.
Right. Or what you could do is add these two together and subtract from 1. Right. Which I would do just because that's less arithmetic. There's less to do there. And I could do that in my head. Bless you. 0.16, so take that away. If you take away 16 cents from $1, you got 84 cents, right? So 0.84. Rather than add 1, 2, 3, 4, 5 things together, I'll add 2 things together and subtract from 1. So we get 0.84. So, based on that probability of 0.84, bless you, would you expect to observe a value of X bar equal to 2 or larger? Yeah, would we expect X bar to be greater than or equal to 2? Yes or no? Absolutely. Right? Equal to 2 or larger. So that's kind of a funny way to say it. I wish it would have said just greater than or equal to 2. But yeah, the probability that it fits this statement is 84% of the time. So absolutely, we would expect that to happen. The probability is not small. It's going to happen a lot more than it's not going to happen. All right? Right, so like I said, nothing is super difficult. It's just very tedious, right? A lot of very small steps, writing out our averages. All right? Nothing super difficult on this particular one. Let's go look at another one. Okay, we haven't done expected value, so let's do this problem as well, just to get an idea. Now remember, expected value, what's our formula for expected value? Somebody tell me? It's probability, right. The sum of its outcome, of the outcome times its probability. Right? Okay. So first of all, it says, consider the population described by the probability distribution shown in the table. The random variable x is observed twice. Find the expected value of x equals a mu. Then use the sampling distribution of x bar to find the expected value of x bar. So first of all, we're just doing it for the entire thing. All right, so let's do it. This one, notice how it says e to the e of x. It doesn't say e of x bar. So we have to find the expected value based on this data. And of course, you could go and open it in StatCrunch and all that. So let's find the expected value of x. Let's write that out. So the expected value of x equals 1 times 0.4 plus 2 times 0.1 plus 3 times 0.2 plus 4 times 0.1 plus 5 times 0.2. And this is important, what we're doing right here. It leads into our discussion for section 6.2. All right, so that's why I like doing this problem right now. Okay, so let's put that in. So I can do most of this stuff in my head, right? 1 times 0.4 is 0.4. 2 times 0.1 is 0.2. 3 times 0.2 is 0.6. 4 times 0.1 is 0.4. And 5 times 0.2 is 1. Right, 5 times 2 is 10, and move the decimal to the left one spot. So it says 0.6, 1.2, 1.6, 2.6. Is that right? Is that what everybody else got? Am I doing that correct? So our expected value is 2.6. Which, wouldn't you think the number in the middle, 3, would be the expected value? But it's not, because of the probability of 1. See how the probability of getting 1 is 0.4? That's higher. That's way higher than all the other 4 probabilities, right? So our expected value is going to be pulled towards 1. Right? Our mean is going to be pulled towards the outlier, towards the 1. So 2.6 is that one. Okay? Now, let's find the expected value of x bar. Now, the nice thing is this chart has already been constructed for you. Right? We didn't have to go through and take each sample and find its mean and then construct its probability. All that stuff's been done for us. Right? The thing we did on problem 3 was construct this table. Right? Now the table's already been constructed for us, which is nice. So let's find the expected value of x bar. And I want you to notice if it's going to be equal to 2.6, less than, or greater than. Right? Let's go ahead and do it. I know that's not very big. Maybe I can make it one step bigger. Now I'll just go ahead and snip it. So we're finding the expected value for x bar. And there's our values. It's a lot better. All right. So I'm going to write pretty small so I can get it all in one line. Expected value of x bar. 1 times 0.16 plus 1.5 times 0.08 plus 2 times 0.17 plus 2.5. I'm still not going to get it all in one line. Plus 3 times 0.22 plus 3.5 times 0.08 plus 4 times 0.09 plus 4.5 times 0.04 plus 5 times 0.04. All right. So let's find this. So the sum, now that I'm not going to do in my head, I'm going to put that in the calculator, right? So 1, just in case I might make a mistake, which is possible, times 0.08 plus 2 times 0.17, which I could have just done this and not wrote it out, but I wanted to really go through this step by step, plus 2.5 times 0.12 plus 3 times 0.22, 3.5 times 0.08 plus 4 times 0.09 plus 4.5 times 0.04 plus 5 times 0.04. And I don't have to worry about doing parentheses in my calculator, because anytime I put the multiplication symbol in between these, it always knows to do all the multiplications before it does the addition. So it does it in order of operations. And then hit equals. And what do we get? The same value. The expected value of x and the expected value of the sample mean are the exact same value. That's good. That's what we want. Right? We want the mean of the population and the mean of the sample to be the same. So that means we've constructed a good sample. There's a special word we'll use for that when the expected value of the population and the expected value of the sample are equal. There we go. All right? And then this next one, the instructor created, is for the median, but it's done in the exact same way. Because since it's 2 points, for 2 values, the median and the mean is always going to be the same number. Right? When you only have 2 observations. The mean of 1 and 99 is 50. The median of 1 and 99 is 50. All right? So anytime you have 2 numbers, the mean and the median are always going to be equal. So this is done in the exact same fashion. All right? So what numbers are going to go in the boxes right here in between? 4.5, 5.5, and tab it? Yeah. 5.5, 6.5. And then you got to go over here and determine which ones have a median of 4, which would definitely be that one, right? And to count up the probabilities. So just like we've done. Okay? Now I want to point out how the mean of the population and the mean of the sample were equal. Right? That's important because that leads into our discussion for today. So let's go in there and do it. Okay, leave page. Okay. Really, the hard part with this section is the notation. We're introducing some more notation here, where we're using subscripts. So once you understand the notation, the actual stats and the math you have to do behind it isn't extremely difficult. The notation's really the hard part. Okay, so here we go. So the title of the section 6.1 was the concept of a sampling distribution. The title of the 6.2 is properties of sampling distributions, unbiasedness, and minimum variance. Unbiasedness. We want our sample mean to be unbiased. Right? When anything's biased, that's bad. Right? Bias is a bad word. Especially in math. I mean, bias is bad in pretty much any context. But it's especially bad when we're talking about math or statistics. Okay. So, let me zoom it in one more time. There we go. The simplest type of statistic used to make inferences about a population parameter. So remember, we're inferring about the data from a population, right? Because we can't actually find the mean from a whole population. It's impossible. Right? We can't find the average weight of every tuna in the Pacific Ocean. It's just not feasible. But what we can do is find a sample right? Construct a sample of tuna, go out and catch 30 or 40 and find their average weight. We use their average weight of the sample we call a point estimator. All right? A point estimator is any of our mean, variance, standard deviation, any type of that data that's used to infer about the population. All right? A rule or formula which tells us how to use the sample data to calculate a single number that is intended to estimate the value of some population parameter. Remember, population parameters are mean, variance, standard deviation, and probability, right, of a binomial experiment. For example, the sample mean x bar is a point estimator of the population mean, mu. All right? That's all it is. Similarly, the sample variance, s squared, is a point estimator of the population variance, sigma squared. So remember the chart that I drew up yesterday? With it had the population, and then it had the sample, and then it had the statistic, and then it had the parameter, right? And the way we wanted to go, M-E-T-E-R. What we wanted to do is go this way, right? In a perfect world, we could pull all of our data directly from the population. In practice, that's extremely difficult, if not impossible. So what we have to do is construct a sample from the population. Then from that sample, we get sample statistics. And then we use these sample statistics to point estimate the parameters, right? Now when I say statistics, they could be x bar, s squared, s, and there's other ones that we won't cover in this particular book. And the parameter, so we use x bar to try and estimate mu, we use s squared to try and estimate sigma squared, and then we use s to try and estimate sigma. Okay, so kind of some fancy language for really not adding anything new, all right? Point estimate is what I call it. Or each of those are point estimators, all right? So here's the definition of a point estimator. A point estimator of a population parameter is a rule or formula which tells us how to use the sample data to calculate a single number that can be used to estimate a population parameter. So we go in here, we somehow construct a single number that we're going to call x bar, and we're going to use that single number, the x bar, to try and estimate the parameter of the population mu. Okay? Now, I know that there's a lot of fancy language in that definition, but it's really a pretty simple concept once you get through all the jargon of statistics. All right? So the point estimator is used to calculate a single number so that we can estimate a parameter. All right? Which is what we're after, right? We're after these parameters. That's what we want to know. Often, many different point estimators can be found to estimate the same parameter. Right? Because I could create a bunch of different samples and come up with a bunch of different x bars from those samples. So I can have many different point estimators, many different x bars that could be used to estimate the same parameter, the same mu of the population. Because each time I go out and catch 40 tuna, their average weight is going to be slightly different. They're not going to be exactly the same. Okay? And that's what that's saying. Many different point estimators. Each will have a sampling distribution that provides information about the point estimator. By examining the sampling distribution, we can determine how large the difference between the estimate and the parameter are. We call that error. All right? What did our sample say? What is it actually in our population? The difference between the two is the error. All right? Or error of estimation. We can also tell whether an estimator is more likely to overestimate or to underestimate. Right? So is our samples of tuna more likely to be lower than the average weight of all the tuna because maybe I'm catching the tuna in an estuary, in a spot where there's younger tuna, right? Where they tend to grow up, as opposed to going to a spot where where it's only adult, older tuna that hang out, and that's where I take my sample from. So that has a tendency to overestimate the true average weight of all the tuna in the ocean. So that's what that's saying, all right? Now what we'll do is we'll find the expected value of each. Just like we did in example 4, just like we did right here. Right, and we found that the expected value of x, which is mu, was equal to 2.6. So we found that our expected value of our sample mean and the expected value of our population mean are exactly the same. They were both 2.6. We would say that those are unbiased, or there's no error. All right? That's good whenever our population mean and our sample mean, the expected values of each, are equal. That's very good when that happens. That's what we're after. All right. Suppose two statistics, A and B, exist to estimate the same population parameter. They could be the means, they could be the variance, they could be the standard deviation. We're going to use a specific variable called theta, which is a circle with a line through it. That represents that it is a point estimator, right? Theta could be any parameter. It could be mu, it could be variance, or it could be sigma, the standard deviation. Okay? And it says etc. because there's a lot of other parameters that we don't cover in this particular textbook. All right? Suppose the two statistics have sampling distributions as shown in figure 6.6. Right? So what you could do back with your point estimator definition that you wrote down, you could put theta in parentheses. All right? Theta will be our point estimator. This would be our theta. All right? Or no, this would be our theta, because it's the population. Right? That's what we're after. Yeah, suppose two statistics, A and B, exist to estimate the same parameter, theta. All right? Okay. As a first consideration, we would like the sampling distribution to center over the value of the parameter we wish to estimate. Right? We'd want the sampling distribution of A, we would want it to be relatively close or to cluster around the population parameter, maybe the mean, maybe the variance, maybe the standard deviation we want to estimate. One way to characterize this property in terms of the mean of the sampling distribution. Consequently, so let's look at a picture more than. If that happens, if our sampling distribution centers over theta, if it centers over the parameter, we say it is unbiased. Right? If the mean of our sampling distribution does not center over the parameter, we say it's biased. And of course, biased is bad. And when it's biased, it can either, notice this sampling distribution overestimates theta, right? Because the mean is greater than theta, so it overestimates. Okay? So write those two pictures down right there. That's very important. Right? And notice theta could be over here to the right as well. It doesn't have to just be to the left. The distance between theta and the mean of our sampling distribution is the bias. How biased is it? Right? All right. So we say it's unbiased if the mean of the sampling distribution is equal to the parameter it is intended to estimate. This situation is shown in figure 6.6a. Now, of course, we would have to know this parameter in order to know if it's equal or not. So it has to be given to us, right? We have to have a value for theta in order to know if the mean of the sampling distribution is equal to it or not. where the mean, notice here it says mu of sub A. It gives us a subscript of A. So that means the mean of the sampling distribution A. Right? Of statistic A is equal to theta. If the mean of a sampling distribution is not equal to the parameter it is intended to estimate, the statistic is said to be biased. All right? The sampling distribution for a biased statistic is shown in figure 6.6b. The mean, mu of B, or mu sub B, which is the mean of the sampling distribution B, is not equal to theta. In fact, it's shifted to the right, so it overestimates. Mu of B, the mean of sampling distribution B, overestimates theta. It's greater than. Right? You can see that biased statistics tend either to overestimate, which mu of B does in this case, or underestimate a parameter. Consequently, when other properties of statistics tend to be equivalent, we will choose an unbiased statistic to estimate a parameter of interest. Of course, we are after unbiased estimators. If they're biased, we've got to kick it out and kind of start over. Go look for another one. Okay? And I know the language in this section is kind of dense, right? When we actually get into practice, it's not nearly as difficult as it might seem at this point. Okay, as it might seem. Really, we'll just run some stuff through some formulas. And we'll see if once we get to the end of the formulas, if they're equal or not. That's all it's going to be. Okay? So let's read. So let's take this paragraph right here and put it in a nice definition. Here it is. If the sampling distribution of a sample statistic has a mean or average equal to the population parameter the statistic is intended to estimate, the statistic is said to be unbiased. So let me kind of rewrite these definitions in a little simpler terms. But you can write down the book definition and then write down my definition as well. Unbiased estimate. So it's an unbiased estimate when mu of A, where A is our sampling distribution, is equal to theta. Now, isn't that a lot simpler definition than all the words that they have written right there? And it's a biased estimate. Oops, same capitalization. And then A is a sampling distribution. A biased estimate is where the mean of A is not equal to theta. Right? If the mean of a sampling distribution is not equal to the parameter, the statistic is said to be biased. And remember, theta can equal the mean, it can equal the variance, it can equal the standard deviation. Right? So theta is the parameter we are trying to estimate. Notice no matter, even if it's the variance, we still use the mean of the sampling distribution. Okay? So I think this is a lot easier way to see it than those two big definitions. All right? And theta could be any of the population parameters. What page has the population parameters? 273. So just a reminder of what a population parameter is. Here they are. There's 4 separate ones that we've learned. There's the mean, the variance, the standard deviation, and the probability of success in a binomial experiment. We need to use the mean of the sampling distribution. So A could be a sampling distribution of the mean. It could be a sampling distribution of the variance. It could be a sampling distribution of the standard deviation. We take the mean of that sampling distribution and see if it's equal to the parameter we're trying to estimate. Okay? And when we see this in practice, it's a lot easier to comprehend, to really understand what I'm talking about. Okay? So that's basically what's in that blue paragraph. Unbiased, the average of the sampling distribution is equal to the parameter. Biased, the average of the sampling distribution is not equal to the parameter. Right? The standard deviation of a sampling distribution measures another important property of statistics: the spread of these estimates generated by repeated sampling. So this sampling distribution of B could be all the samples of the standard deviations. All right? So the standard deviations of all my samples, I would create a frequency histogram. And I would expect all of my standard deviations to start to cluster around a certain point. All right? The average of the standard deviations, and I know that's kind of weird because we're mixing two things together, but if I perform an experiment 100 times, I'm going to have 100 different standard deviations. Then I need to average all those standard deviations. All right? That's what's going on here. And I would expect the average of that standard deviation, of all those standard deviations, to be very close to the actual standard deviation of the entire population. Right? That's what this is saying. Right? Suppose two statistics A and B are both unbiased. Notice they're both unbiased because they fit this definition. The mean of their distribution is equal to the parameter, which in this case they both are. Which one of those do you think you would rather use, though, A or B? If you had a choice, would you rather use statistic A or statistic B? Even though they're both unbiased, which one would we prefer? What do you guys think? A, why? Because it's a lot narrower. There's a lot less variation. It's clustered a lot closer to the parameter value. There's less spread. All right? So the chances, basically, notice the area. I mean, B has a lot of area out here that's outside the curve of A. So there's a lot of other values that B could assume that A doesn't even have a chance of assuming because it's not there, right? The graph doesn't go out that far. So since the means of the two sampling distributions are the same, we turn to their standard deviations in order to decide which will provide estimates that fall closer to the unknown parameter. Naturally, we will choose the sample statistic that has the smaller standard deviation, which means less spread, right? Note that the standard deviation of distribution A is smaller than the standard deviation of distribution B. That's because it has less variation. Remember, standard deviation is a measure of variability, indicating that over a large number of samples, the value of A cluster more closely around the unknown population parameter than do the values of B. Stated differently, the probability that A is close to the parameter value is higher than the probability that B is close to the parameter value. That's because the area under the curve is closer to the parameter value in A, right? There's a lot more area under the curve in A that's close to the parameter than there is in B. That's what that means. In sum, to make an inference about a population parameter, we will use the sample statistic with a sampling distribution that is unbiased, which both of those are unbiased. Both of them have a mean equal to theta, but also has a small standard deviation. And if two sample statistics are unbiased, we would look at their standard deviations and pick the one that has the smaller standard deviation. Okay? And I know this is a very abstract topic, once again, that we're talking about. We're finally going to get to an example. Okay? Will not concern us because the best statistic for estimating specific parameters is a matter of record. We will simply present an unbiased estimator with its standard deviation for each population parameter we consider. The standard deviation of the sampling distribution of a statistic is also called the standard error of the statistic. Right? That's just in a note, so that's not something I'm going to ask you about. That's just something you might see somewhere else. Right? Okay. Refer to example 6.1 and the outcome X of a $5 wager in craps. So let's go back to the example we covered in class yesterday. This is just on the come out roll. All right? So just the very first time you roll. If you roll a 2, 3, or 12, you lose. Your probability of rolling a 2, 3, or 12 is 1/9. If you roll a 7 or 11, you win $5. Your probability of rolling a 7 or 11 is 2/9. The reason this is so much higher than this one is because of 7, right? 7 has the most ways of making that number when you roll 2 dice. Right? There's actually 6 different combinations if you don't allow repeats. Right? 1, 5, 5, 1, 2, 4, 4, or no, 2, 3, 3, 4, 4, 3, and 6, 1, 1, 6. So 1, 6, 6, 1, 2, 5, 5, 2, 4, 3, 3, 4. And then any other number, so 4, 5, 6, 8, 9, 10, 11, 8, 9, 10, excuse me, not 11, you would break even. You would have to keep rolling. Right, so there's that. And then we went and constructed all the different possible outcomes of 3 rolls. Right, if I did 3 come-out rolls. So I put together all the different combinations. I could lose all 3 times. I could lose twice and then break even. I could lose, break even, and then lose. Right, and that was all listed on. So just kind of as a, to re-jog your memory, 276. Let's just go look at it. And here it is. So the chances that you crap out 3 times in a row is 1 out of 729, which is not very good, right? It's 0.1%. Probability that you crap out twice in a row and then roll a point, which means 4, 5, 6, 8, 9, or 10, is 6 out of 729. And here's all the different probabilities. The highest probability is you rolling a point all 3 times. You neither crapping out or winning. And the chances of that happening are 216 out of 729, or about a third. Right, about a third of the time. Right? Close, not exactly a third. It's a little less than a third, but pretty close. And then, of course, your chances of winning all 3. So your chances of rolling a 7 or an 11 3 times in a row is 8 out of 729. Right? We multiply the probabilities together because the outcomes are independent. Okay? So what they do is exactly how we started class off today. They took all the different possible means. There's actually 7 different values that the mean can be. Right? 7 different values it can assume. Then it adds the probabilities together of each different mean value. Let's go back to 280. Bless you. That's 280. So there's a little review of how they came up with this chart. And then they did the same for the median. The median can only assume one of 3 values. Right? 25 out of 729 times, your median was -5. 612 out of 729 times, your median was 0. And 92 out of 729 times, your median was 5. Which one of these is a better estimator of the population parameter? Is it the mean or the median? Now, we've seen in most cases it's going to be the mean. But for, say, housing prices, it's the median. Right? The median housing prices is a better estimator of the population parameter. Right? So let's read this question. The sampling distribution of X bar and M were found to be as follows. Show that X bar is an unbiased estimator of mu. Show that X bar is an unbiased estimator of mu. So now I'm erasing theta and I'm actually finding mu. And then I'm erasing mu of A and I'm finding actually the mean of my X bar. Right? So now I'm going from general to a specific example. So remember, theta can be any parameter. In this case, theta is the mean, all right? Or the mu of the population. So I have to find the expected value of x, and then I need to find the expected value of x bar and see if they're equal. All right? That's all that's saying. Okay? I don't want to give it away. I'll fucking roll down here. Okay. So let's do it. So let's find the expected value of x, which is equal to the population mean. And then let's find the expected value of x bar. All right. So the expected value of x is equal to mu. Right? That's how it's defined. So we're finding mu. And then we're going to find the expected value of x bar and see if they're equal. If they are equal, then it's unbiased. So the expected value of x, which is equal to mu, is negative 5 times 1/9 plus 0 times 6/9 plus 5 times 2/9. What does that equal? I don't even have to worry about the first one, right? Or the middle one, excuse me. So it becomes negative 5/9 plus, this is just 0, right? Because 0 times anything is 0. Plus 10/9. Right? 5 times 2 is 10 over 9. So what does that equal? 5/9. Which is what as a decimal? Which is approximately 0.56, we'll call it. It's 0.5 repeating. Another way you could see it, which you guys might have seen at some time in your life, is the 0.55 with a line over it. Have you guys seen that to represent a repeating decimal? So same thing. So I'll go ahead and write that. Okay, so now let's find the expected value of x bar, just like we did on our homework that I showed you today. Right? Just like we did on problem 4. So the expected value of x bar is x bar times p of x plus this x bar times p of x, right? All the way down. The sum of x bar times p of x. Right? It's the sum of x bar times p of x bar. And this is the sum of x times p of x. Let me go ahead and write that in. So E of x equals mu, which equals the sum of x times p of x. The expected value of x bar equals the sum of x bar times p of x bar, which they'll call the mu of x bar. They'll use an x bar as a lowercase, or as a subscript. So this is the mean of the sample mean. This is the mean of the population. Right? So let's write it out. So it's equal to negative 5 times 7 over, or 1 over 729, excuse me. Plus, I'm going to go ahead and do minus instead of plus since it's a negative. 3.33 times the probability of negative 3.33. 18 over 729. Minus 1.67 times 114 over 729. Plus 0 times 288 over 729, so we don't even have to worry about counting that one. All right, plus 1.67 over 228 over 729. This is definitely not something you'd want to do in your head, right? If you could probably go make millions somewhere, like guessing numbers and stuff like that. And then plus 5 times 8 over 729. And some of your calculators will actually find the expected values. Yeah, watch. I'm going to show you how to do it in the calculator. Oh, I think you have to enter in the probabilities. Yeah, I'm not, I'd have to play with it a little bit before I get it exactly right. So let's just do it brute force. So let's punch that in your calculator, all right? So -5, I'll go ahead and show you. Okay, so -5 times. Now here, you have to make sure that you put your fraction in parentheses. Because what if I do this right here? 5 times 1 divided by 729. What's going to happen there? It's going to do -5 times 1, which in this case won't make much of a difference, all right? But you got to just kind of pay attention to what's going on here. Because you want to make sure that if you miss something that you don't have an order of operations error. Which in this case you won't. Right? But I just wanted to make you aware of that. So it really won't make a difference. Because you want it to all be in the numerator anyways. Right? So -3.33 times. No, you don't need the parentheses. I'm just making you aware though that you could at some point, depending on how you type this in. Because what it's going to do is it's going to do the multiplication and then divide it by 729, which is fine. That's sound. So you don't need the parentheses here. Divided by 729 minus, and I'm putting minus instead of plus because they're negatives. 1.67 times 114 divided by 729. So right there, we don't care. So it's fine to do that multiplication first and then divide by 729. That's completely fine. Right? And I'm just going to go ahead and skip the 0. There's no reason to even calculate this piece, right? Because it's just 0. So I'm going to move on and do plus 1.67 times 228 divided by 729. Now, be careful if some of your calculators don't do order of operations, then you have to do the parentheses. But these TI calculators do. Plus 3.33 times 72 divided by 729 plus 5 times 8 divided by 729. Oh, I haven't even done the population mean yet. That one's easy, though. So here's our sample statistic. Oh, I did do it. What am I talking about? I did it by hand. So here was our population parameter. There's our sample statistic. Now, they're not exactly equal if we go out to 10 decimal places, but to 2 or 3 decimal places, they are equal. Everybody see that? Because even if I rounded this and I called it 0.56, round this number to 2 decimal places, and what is it? 0.56. So therefore, X bar is an unbiased estimator of mu. Mu of X bar, mu of my sampling distribution, which is exactly what I'm saying here, right? That's in general, so I just showed that mu of X bar was equal to mu. Check. We showed that it was unbiased. So this is in general, and this is a specific example. Right? That's it. So now let's do the same thing for the median. Now, for the median, there's nothing I need to do here with the population parameter mu. I've already found it, right? So the answer to part A, let me go ahead and roll down. So here's A. The expected value of a discrete random variable x is defined as the sum of x times p of x, where the summation is over all values of x. So the expected value of x, which is called mu, is the sum of x times p of x. which we found to be 0.556 or 0.56, depending on how many decimals you round it to. The expected value of the discrete random variable x bar is the sum of x bar times the probability of x bar. So there's the exact thing that I have written on the board, right? And we notice that these two values are equal. It is an unbiased estimator. So this is a fine example right here of the terminology and the wording being a lot more difficult than it actually in practice. In practice, it's really not too bad. You just find the expected value. All right? So now let's do it for the median. So I've already done this part. Right? So now I want to see if the mean of the median is equal to mu. So my next question is, so the way to answer part B says, is the mean of the median, and those are two different values. One's a mu, one's the median. So let me rewrite it a little bit. Is mu of the median equal to the mu of the population? And that's a capital M for median, which is a subscript. Okay? So I've already found mu, right? The expected value of the population is 0.556. That's not going to change. So let's find the expected value of the median, which is going to be the sum of m times the probability of m. So this is going to be equal to -5 times 25 over 729 plus 0 times 612 over 729 plus 5 times 92 over 729. So this is equal to the average mu of the median, as opposed to the average of x bar. So what is this after we put it in the calculator? All right, so it becomes -5 times 25 divided by 729 plus, and I won't even put 0, right, because it's just 0. So plus 5 times 92 divided by 729. So there it is. So this is my, and there's a negative here, but you can't see it. And I didn't put the 0 in because it doesn't change anything, right? So -5 times 25 over 729 plus +5 times 92 over 729 and hit equals. What is that rounded to 2 decimal places? 0.46. So our conclusion is, no, it is not an unbiased estimator because the average of the median is not equal to mu. Since they're not equal, it is a biased estimator. Does it overestimate or does it underestimate mu? It underestimates because 0.46 is less than 0.56. So it underestimates. All right. And here we go. B. The expected value of the sample median M, the expected value of the median M. Another way to say that is the mean of the median, right? Because the expected value is equal to the mean. Since the expected value of M is not equal to mu, the sample median M is a biased estimator of mu. The reason it's biased is because this value is not equal to that value. Okay, let's do the variance now. So now, instead of our theta being the mean, we're going to let it be the variance. Right? Right. Refer to example 6.4 and find the standard deviations of the sampling distributions of x bar and m. So refer to example 6.4, which is the one we just covered, right? The variance of the sampling distribution of x bar, we denote it by the symbol sigma squared of x bar. So this is that funny notation I was talking about. So it's sigma squared and it has a subscript of x bar because that's the distribution it's describing. Kind of how here I put a subscript of the median of MED. So this is the mean of the sampling distribution of the median. All right. So here's our formula for variance once again, which is the sum of the difference between x bar and the mu squared times the probability of x bar. Which that's the long formula, that's not the shortcut formula. Right? Okay. So from example 6.4, we know the mu, or the expected value of x bar, is 0.556. All right, that was what we found out right on this one. Right, here's that number right here. We just found it. It was 0.56. The expected value of x bar was 0.56 after doing all the math. So let's find the variance of x bar. Right? So let's find the variance of x bar. I'm going to do it on the next page, on the next board. So the variance of the sampling distribution x bar is equal to the sum of my x minus mu, or each of my x bars minus mu, squared, times the probability of achieving that given x bar. And x bar goes from, what was the smallest value? -5 to +5? Right, it's -5, -3.33, -1.67, 0, +1.67, +3.33, and 5. So let's go back and look at this chart and find the variance. So this isn't using the shortcut formula. We're going to do it here using the longer formula. Right? Remember, there's always two separate formulas for the variance. Okay, so this is equal to x bar minus mu, where mu, since x bar is an unbiased estimator, we're going to go ahead and say mu is 0.556. Right? So it becomes -5 minus 0.556 squared times the probability of x bar, which is 1 over 729. So we're finding the square difference of each of the x bar values. And I'm going to go ahead and just put plus here because I'm squaring it. -3.33 minus 0.556 times squared times the probability of x bar being -3.33, which is 18 over 729. Plus -1.67 minus 0.556 squared times the probability, which is 114 over 729. Plus, now I will write the 0 down because it will be a value. 0 minus 0.556 squared times 288 over 729 plus, now do the other three, right? The 1.67, the 3.33, and the 5. So 1.67 minus 0.556 squared times P of X bar, which is 228 over 729. That other one was 288, right? Yeah, 228. Plus 3.33 minus 0.556 squared times the probability of X bar being 3.33 is 72 over 729. Then there's one more, right? Plus 5 minus 0.556 squared times the probability that X bar is 5 is 8 over 729. You'll notice all of these terms will be positive. Even though this in here is going to be a negative number, when I square it, it turns it positive. Do you see that? So it's negative 5. So it's X bar minus mu squared times probability of X bar. X bar goes from negative 5 to positive 5. So there's my first X bar, my second X bar, my third X bar, my fourth X bar, my fifth X bar, my sixth X bar, and my seventh X bar. That is definitely something you would want to do on your calculator. StatCrunch would come in handy right here. After all that calculation, let's verify that it's 2.675. So I want everybody to put that in their calculator and make sure they come up with that value. All right? So, open parenthesis. You've got to have a lot of parentheses here. Negative 5 minus 0.556 squared times.
You put the parenthesis and then the square?
Yeah, the square's got to be outside the parenthesis. Yeah, let me show you. Good question. Let me put it on the document camera. So see how the square is outside? So here, let me just start over. So I'm going to go open parenthesis, negative 5 minus 0.556, close parenthesis squared. Do not do this. Do not put squared close parenthesis. Why?
Because it's going to square the 0.556.
It's not going to square the entire difference, right? That's going to return a negative value. Variance can never be negative, right? Variance is distance from the mean. Because look at what happens now when I put it negative 5 minus 0.556 and then square the value. Look, it gives me a... Look how different those two numbers are. Oh, I put minus too many times. Hold on. Let me go delete, clear. So let me do it wrong. So that's the wrong way. Look at the difference between those two numbers. And that's only because of where I put my square. See, look at those. One, if I put the square inside the parentheses, it gives me a negative value. When I put the square in the right place, it gives me a positive value. Big difference. All right? So now let's do it. Okay, start over. Okay, so we have, open parenthesis, negative 5 minus 0.556, quantity squared, times, and you don't have to worry about the parentheses here on the probabilities, because it knows that all this stuff is in the numerator, and then it divides by 729. Plus, open parenthesis, negative 3.33 minus 0.566, close parenthesis squared, times... What is it? Oh, I have a book right here. 18 over 729? Yeah, that's right. Times 18 divided by 729. Plus, open parenthesis, negative 1.67 minus 0.556. Close parenthesis squared times 114 over 729 plus open parenthesis 0 minus. Did I? Oh, it's 114? Oh, yeah, see? See, and this is the tedious stuff I'm talking about. You know, you miss one thing and it messes up everything. There we go. Does everybody know how to go back and enter in a number if you forgot something? Hit the second insert and go to wherever it needs to be and click the number and it'll push everything else over rather than replace, which is very nice. Like in this case, I didn't have to start all the way over. So plus 0 minus 0.556. Close parenthesis. I hope my calculator does this. Times, what was the probability of 0? 288 over 729. And look, my calculator's stopping right there. So what I'm going to do is just add to the answer. So I'm going to delete off. I'm going to go back to here. I'm going to hit enter. Now, if you have the big calculator, you don't have this issue, but if you have the smaller calculator, you do. It won't let you put everything on one line. So there's enter. So this is just the sum of the first three pieces, right? The first three terms. So now I'm going to start, I'm going to go plus and then start from there, right? So plus, open parentheses, 0 minus 0.556, quantity squared.
Okay, I see.
Yeah, you see what I'm saying there?
My answer's not the same as yours.
For the first three terms? Oh, it's not? Well, let me go through and make sure I got the same thing as a book, because I might have made a mistake. And then 0 is 288 times 729, divided by 729. Plus, open parenthesis, 1.67 minus 0.556, close parenthesis squared, times 228, divided by 729. 729. Plus, open parenthesis, 3.33 minus 0.556, close parenthesis squared, times 72 over 729. One more. Plus, open parenthesis, 5 minus 0.556. Hopefully I don't run out of room here. Times, what was it for 5? 8 out of 729? Ah, dang it. So I'll just go back and I'll just do the very last term. So I need to go plus, open parenthesis, 5 minus 0.556 quantity squared times 8 out of 729. .67, I'm off by just a little bit. I might have done 5.566 somewhere. Because here's what the book has. I have 2.678, and they have 2.675. So somewhere along the line, I must have punched the wrong thing in the calculator. And this is what I'm talking about with the tediousness. This is maybe where StatCrunch would be a lot more useful, all right? Or even Excel, all right? So I could go back and look at my calculator and determine where I made an error. So negative 5 minus 0.556 squared times 1 over 729. Oh, that's right. So 114 was for the negative 167. Oh, I see where my error is. look what I subtracted right there. Right here. That's 0.566 instead of 0.556. So it didn't lead to a huge error at the end, but it still made a difference. So that's where I was off by a little bit. But you guys get the idea of what to do. And I'm trying to do this a little faster so that I can, get through all this stuff. When you're doing it on your homework, you can do it a lot slower. Really, I would even advise you to do it one by one. Do this piece right here, hit enter. Then do plus this piece, hit enter. Then plus this piece, right? Because it'll keep a tally. Rather than trying to do it all in one line like I did and make a stupid error like that. All right? Now on a test, if you had all this written out, you showed me your math, you showed me the way you went through it, and then you missed it by 1 decimal like that, you guys have noticed I wouldn't kill you for that. You'd miss maybe one point out of 5 or 1 out of 7. All right? But something that simple led to a little bit of error at the end. Well, let's go back to the book and finish it. Okay. So let's say I didn't make the error, and that's my variance. Then the standard deviation is just simply the square root of it. All right? And then it does the same thing for the median. But notice the mean it uses for the median was the expected value that we came up with. That was actually wrong, right? It was a biased estimator. Oh, I erased the median. It was on this one. So see what it uses for? It uses the expected value of m, which was 0.46, right? That's what we found out. So here's my variance for the median is each value minus the expected value. Oh, they're missing something on that. You guys see what they're missing? The squares. This textbook's had a couple errors. Yeah, this needs to be squared right here. That needs to be squared. That needs to be squared, and that needs to be squared. They have it right here in the formula, but they didn't do it in practice. So let's do it squared and see if we come up with 3.801. So let's do it correct. So clear. Okay, so open parenthesis. -5 minus 0.46, close parenthesis squared, times 25 divided by 729. Plus, open parenthesis, 0 minus 0.46 quantity squared times 612 divided by 729. Plus, open parenthesis, 5 minus 0.46 quantity squared times 92 divided by 729. Yep. That's what we get on the calculator when we square it. So they've made, there's an error in this textbook in that notation. Yep. Each of these values need to be squared. Squared, squared, squared. And then the square root is 1.95. So what does that tell us?
So we're getting the square root or the variance
Of the median.
of the median down here and up here. And we're getting the square root of the variance
Of the sample mean. Right. So we're doing, the first one we did, this is the standard deviation of the sample mean. This is the standard deviation of the sample median. So this one, and this leads back to us saying, what if these both would have been unbiased estimators, right? What if they both would have had the mean equaling 0.556? Then which one would we pick? We'd pick the sample mean because it has a smaller standard deviation. And that's going back to that one picture we looked at that had the two separate curves that had the same mean, but one was more spread out than the other. The median is more spread out because its standard deviation is 1.95. The sample mean standard deviation is 1.64. Which statistic appears to be the better estimator for the population mean mu? The sample mean or the median? To answer this question, we compare the sampling distribution of the two statistics. The sampling distribution of the sample median M is biased, and its standard deviation is 1.95. And it's larger than the standard deviation of X bar. Consequently, the population in question, the sample mean X bar would be a better estimator. And really, we didn't even have to go check the standard deviation to know it's a better estimator. We knew it was a better estimator right here. Right here at this point. Because one's biased and one's not. We would rather use the unbiased one before we use the biased one. But if this happened to be 0.556, then we would want to go look at the standard deviation. So we want it to be unbiased and have a small standard deviation. Okay? Okay. Let's go look at a homework assignment. Or homework problem. And like I was saying before, this chapter, it really seems a lot more complicated than it is when we actually get in there in practice. Right? The math behind it is tedious, but it's not super difficult. So let's go look at 6.2. So due by midnight tonight is 6.1. Due by midnight tomorrow night is 6.2. So let's go ahead and preview it. And come with questions in class tomorrow. All right, so let's go ahead. I don't really want to do... let's go ahead and just do the first one. Not that big a deal. So this has parts A through E. It's got 5 different parts to it. Each question. So even though there's 5 questions, let's do that in the search. Okay. Consider the following probability distribution. Complete parts A through E. So you guys do that. Find the mu of the population. Find the population mean. So that's the expected value. So first of all, you would expect this expected value to be pulled towards 5. You guys see that? Because the probability of 5 is 1/2. So I would expect it to be closer to 5 than it is actually to 0 and 1. Or maybe in the middle, but one observation is making it in the middle compared to 2 observations. Because that one observation carries a lot of weight. So expected value of x is equal to mu, which is equal to the sum of x times p of x. So, expected value of x equals 1 times 1, or 0, excuse me. 0 times 1/4 plus 1 times 1/4 plus 5 times 1/2. Which equals, that's just 0, right? 1 times 1/4 is 1/4. 5 times 1/2 is 5/2, which is equal to 0.25 plus 2.5, so it's 2.75. You guys agree with that? And if you're not sure, just punch that in your calculator, exactly as it appears. All right, so go in there and do it. 0, even if you didn't see the 0, 0 times 1/4. And you don't even need the parentheses, right? 0 times 1 divided by 4 plus 1 times 1 divided by 4 plus 5 times 1 divided by 2. There we go. 2.75. So that's our mean. Notice how that number is being pulled towards the 5, right? It's being pulled towards 5 because of the probability of 5 is 1/2. All right, so let's go in and put it in. So my mu is 2.75. There we go. Find the variance. So you can either use the shortcut formula or you can use the long formula. Right? It's x minus mu, right? So let's find the variance. So I know mu is 2.75. So it's the difference of each the square difference between each observation and mu times its probability. So the variance equals the sum of x minus mu squared times the probability of x, right? And if you're not sure, it'll be listed right here in your, if you go to view an example, it'll step you through how to find that, and there it is. Right? So the variance is equal to the sum of the difference squared of each observation from the mean times its probability. Right, so let's go back here. Minus 2.75 exactly. So it becomes equals 0 minus 2.75 squared times, what was the probability of 0? 1/4. Plus 1 minus 2.75 squared times 1/4. Let me rewrite that a little bit smaller so I can get it all in one line. Plus 5 minus 2.75 squared times 1/2, right? So let's go back to the document camera. So we have, open parenthesis, 0 minus 2.75 quantity squared. Make sure you put that squared outside the parentheses. Times 1 divided by 4. Plus, open parenthesis, 1 minus 2.75 quantity squared times 1 divided by 4. And if you want to put this fraction in parentheses, you can. Putting more parentheses in is not going to change anything. All right? Plus, open parenthesis, 5 minus 2.75 quantity squared times 1 divided by 2. And hit enter. 5.1875. Is that what everybody else got? So then what's sigma going to be equal to? The square root of it. Right, the square root of 5.1875. So I'm going to go second square root. So I'm going to hit the second key, square root, and then hit second answer. Or I could retype that decimal. But it's a better rule to get into, a better habit to do answer in case this decimal is really long. So that you pull all the values in. And then there's my variance and standard deviation. So let's type those in. So it says round to the nearest thousandth. So what's the variance rounded to the nearest thousandth? 5.1875? Right? So what's that rounded to the nearest thousandth? 188. Okay. So, now is where we need to go ahead and list all of our observations. Now, to make sure you don't forget one, you're welcome to use the View an Example tab just to make sure you don't forget an observation. Because what are all these going to be? They're going to be 0, then it'll be 0.5, then it'll be 1, and then we'll have to worry about the other ones, all right? So what I want you to do is, you're fine with going through this. So here's all the possible samples. So basically you would take this, and everywhere 3 appears, you would put 5. All right? So here's all your different means for that case. Now notice that this example, in the viewing example, the numbers are different. Right? They're 0, 1, and 3 instead of 0, 1, and 5. So our possible samples will be, let's go ahead and write them out for this case. So that would be 0, 0, 0, 1, 1, 0. 1, 1. And really, you know, I would, if it was me, I would like to do this in a different order. Now I would put 0, 5, and then 5, 0, if it was me. That's how I would like to do it. Right? Because now I've exhausted, this is all the combinations that include 0. So now all I have to do is worry about the 1 and 5 and the 5 and 1. Right? So then I have 1 and 5, 5 and 1, and then finally 5 and 5, and that's it. 1, 2, 3, 4, 5, 6, 7, 8. 1, 2, 3, 4, 5, 6, 7, 8, 9. Which one am I forgetting here?
1 and 1.
Do I not have it? Oh, I don't have it. Yep. 1 and 1 I'm forgetting. So let's just throw it in there. And you can always verify how many there needs to be based on that, right? Based on kind of this chart, and if you go through this systematic approach here. So I like to do my doubles, then 0 with 1, 1 with 0, 0 with 5, 5 with 0. And really I would do 1 with 5, 5 with 1, and then I should have done 1 with 1, but it doesn't really matter. Now what's the mean of each of these? So here's my samples. What's my x bar for 0, 0?
0.
0. What's my x bar for 0, 1? How'd you come up with that, Oscar? How'd you come up with that number?
0 plus 1 divided by 2.
Right, 0 plus 1 divided by 2. Same thing for 1, 0. What's the mean of 0, 5? 2.5. So the mean of 5, 0 is also going to be 2.5. 1, 5, what's the mean going to be? 3. 5, 1? 3. 5, 5? 1, 1? 1. All right, now we need to multiply all those together. Now, what did it say above? So now I need to come up with the probabilities of each. So now I can come in here to this and write in all my possible values, all my possible means. So I have 0, 0.5, 1, 2.5, 3, and 5. So this will be 2.5, 3, and 5. Now we need to figure out the probability for each. And the way you do that is, since they're independent, you just multiply the probabilities together. So what's my probability of getting a 0 and then another 0? How would we do that? What's the probability of getting a 0? So if it's independent, if I get a 0 and then the next time I get a 0 and they're independent, what do I do to the probabilities? Remember? Multiply them. So if this probability is 1/4 and this probability is 1/4, it's 1/4 times 1/4, which is 1/16. It says do not round. So I don't know if they want 1/16 or they want the decimal equivalent. Let's go through and do the rest of them. So 0, 1 is going to be the same thing, right? Because both the probabilities are 1/4. So this one's going to be, let me draw a line, 1 out of 16. This one's going to be 1 out of 16. Does everybody agree? what's going on here? Because they're independent events, so I multiply their probabilities together. And that's what it says right here. Right? The sample mean x bar, random sample of n equals 2 measurements from this distribution. Put the answers in ascending order for x bar. So what's my probability of getting a 0 and a 5? What's my probability of getting 0? What's my probability of getting 5? What's 1/4 times 1/2? 1/8. So this one's going to be 1/8. And so is 1/5 is going to be 1/8, right? Because it's 1/4 times 1/2. Same thing with 5/1. It's going to be 1/8. My probability for 1/1 is going to be 1/4 times 1/4, which is 1/16. What's my probability for getting 5/5 going to be? 1/4. 1/2 times 1/2. Let's go ahead and put them in. So what is 1 out of 16? I'm just going to go ahead and type the fraction. So 1/16 for 0. So now my probability of 0.5 is this plus this, right? Because 0.5 appears twice, which is 2/16, which simplifies to what? 1/8. And then 1, how many times does 1 appear? Just once, right? It's 1/16. I wonder if it'll allow me to do 2/16. Let's try it, because then I can always go back and change it. Because I'm going to add together all the numerators and make sure they're 16, right? So that our probability, this all needs to sum to 1 still. How many 2.5s are there? 2. 1/8, which is 2/16, and 1/8, which is 2/16, so 4/16.
You're adding the 1/8 and the 1/8 together?
Yes, which is 2/8, which is equivalent to 4/16. The reason I'm doing it this way is because I want to, at the end, I'm going to add all my numbers in the numerator together and make sure it adds to 16, so my probability is 1. Does everybody see that? So it is probably a little bit easier to, which is equal to 2/16. This is 2/16. This is 2/16, which is not a reduced fraction, which kind of like, to me, it's even hard to even write that down because it's not reduced. You know, you're always taught to reduce a fraction. 1/4 would be 4/16. So I have all of them in terms of 16 now. So my 3, how many 3s are there? There's 2. How many 16ths are there? 4/16. And then 5 is what? 4/16 as well, right? So let's add all those numerators together. What do we get? 4 plus 4 plus 4 is 12, 13, 14, 15, 16. That's good. Because our probability has to sum to 1. Now, I don't know if it's going to get counted correct. It might want, yeah. So it probably wants a simplified answer. So let's take that back to 1/8. This one back to 1/4. This one back to 1/4. And this one back to 1/4. There we go. Okay? There's still a few more parts to this, but we're out of time. Is X bar an unbiased estimator of mu? How do I answer that question? What do we have to do there? Remember from our textbook, if X bar, if the expected value of X bar and mu are the same, then it's unbiased, right? Going all the way back to what I erased off this. It's unbiased if mu of that A equals theta. So let's find the expected value of X bar real quick and see if it's equal to 2.75. Let's punch that in the calculator. So you don't have to worry about the 0 times 1/16. Right? So do 0.5 times 1 divided by 8 plus 1 over 16. I don't even need to do the multiplication there. plus 2.5 times 1/4 plus 3 times 1/4 plus 5 times 1/4. And hit equals. And what do we get? So therefore, yes, it is an unbiased estimator for mu. And then you do the variance. Which that you would do x bar minus mu, right? You do the x minus x bar like we did in the book for the craps table. But I got to stop right there. That's the rest of the class. So what I want you guys to do is go home and work on this homework and come with questions tomorrow. Right? We only have one more section to cover in this chapter. And we'll finish it tomorrow with your questions. That should be just enough time. So that'll be perfect. Then we'll review next Monday, and the test will be next Tuesday on 7/7. The lucky day, 7/7. Right? All right, guys. Where's my sign-in sheet at? Right here, make sure you sign it before you leave. And have a great day. Okay, yeah, I'll take it. Thank you. So remember, this section's not difficult, it's just tedious. Very tedious. Yeah. Let's go and send that out. Blue and black.
What happens to the bosses to get the eyeball space in your office? Did you see it?
I don't think so. But I'll look again if I did. If you did, I'll. Okay. Yeah, excuse me.
So I talked to my career counselor yesterday.
Yeah.
And she said that usually they'll give you like 90 days before you have to report, so I should be.
Oh, after you're made aware, you have 90 days?
Yeah.
Oh, okay. So you should be good then. Okay.
Yeah, as I told him, man, I was like, this is my second time taking this class, I really don't want to take it over again.
I know, especially when you know what I mean, when you're doing well, and
Yeah.
all you got to do is finish, you know. But yeah, so next week you'll be here for sure. I mean, it shouldn't be a problem, right? Is that what you're saying? Okay.
So,
Well, that's good. We'll see you tomorrow.
all right, see you.
I was wondering if you could help me. I wasn't here yesterday, so I didn't get to
Okay.
turn in that other paper.
The Z-Sport worksheet?
Right,
Okay.
but I was wondering if you could help me figure out the easier way to do things. Because like I did my homework, and I just did it by the examples, not really drawing pictures. So
Right.
I'm still a little bit confused with the drawing pictures. And I
Okay.
did some of them, but...
Well, yeah, let's go tomorrow.
Okay.